Okay, please take a moment, read through this problem, look at the graph, come up with your ideas about what you think each will be, and then continue watching the video so we can start nailing it down together. All right, the first thing I'm going to look for here is the absolute maximum. Now, the absolute maximum means that it's the maximum for the entire thing. Well, you'll notice that we actually have 2 points here that are at an absolute maximum. Both of these reach the exact same height. And so both of those would actually be considered to be the absolute maximum. So those are both, B and F, the absolute maximum. Absolute minimum. How low does the entire graph go at any given point? And so this is E. The absolute minimum occurs here at E because that's the lowest that the graph goes. Now we're looking at a local maximum. A local maximum is the maximum in a certain given area. So like if I segmented this graph up a little bit into some pieces, like between those 2 marks, you'll see that B is the maximum between those two. But if I then head over here, notice that D is the maximum between those two. That means D is also a local maximum. But what about F? Well, it is the maximum between there and where? Like here? But there's no graph out there, right? So because there's nothing out there, F is not actually considered to be a local maximum. It can be the absolute maximum, but it's not a local maximum because there's nothing to the right of it. And finally, for the local minimum, A, nope, not a local minimum because there's nothing to the left of it. C, yes, C is a local minimum because between these 2 sections, that's as low as the graph goes. What about E? E is also an absolute minimum. Can it also be a local minimum? Yes, it can. And so the thing to remember coming out of these is that a local max or min must be the max or min from both sides. Not just one side, but from both sides. Now, with that in mind, here's some notes to take down. This is actually the formalization about how we find and determine whether something is an absolute or a local maximum or minimum. By the way, the maxima and minima are together described as the extrema, that is the extremes of the graph, just extrema for the plural there. But go ahead and add this into your notes and then proceed into the next page after that. So with what we've seen about the absolute extrema and the local extrema, take a look at this please and figure out where are the absolute max and min and where are the local max and min values. All right, so let's start with the absolute max. So looking at our graph here, we can see that the highest this graph goes is right up here. So what is the highest that this graph actually reaches? And if you said 5, close, but not quite, because you notice it's an open dot up there. It's approaching 5, but it's never actually reaching it. Okay, so what about 4.9? Well, no, it gets bigger than 4.9, right? 4.99? No, it gets bigger than that. In fact, it gets infinitely close to 5, but it never actually reaches it. And so for that reason, we actually list nothing for the absolute maximum. Okay, what about the absolute minimum? There is one of those. And so we can see that that is going to happen right here. And that's going to be at the point 4, 1. Next up, let's look for the local maximum, or local maxima, as it'll turn out to be. So what about here? Is that a local maximum? No, because it's not the maximum from both sides. Okay, so then do we have a local maximum here? No, because again, we don't have a single value that's higher than all the values around it on both sides. Okay, so then what about here? Yes, that would actually work. So then that looks like that point is going to be at 3, 4. So we have a local maximum at 3, 4. Okay, as we keep going down, what about right there? Yeah, it looks like we got another local maximum right there. And so that's going to be at 6, 3. All right. Next up, how about any local minimum? All right, so then, is this point then a local minimum? Well, it is the minimum as we look at it from the left-hand side, but it's not lower than the values on the right-hand side. So no, that is not a local minimum. What about this point right here? Is it lower than all the points directly to its left? Well, yes, it is lower than those. Is it lower than all the points directly on its right? Yes, it is lower than those as well, which meets our definition for a minimum. So we will say that that is, yes, a local minimum there at 2, 2. All right, next up, we had our absolute minimum over here. Notice we can get there as the minimum from both sides. So that is also going to be a local minimum. And then what about this point? Is that going to be a local minimum as well? No, because while it is lower than all the points on the left, there are no points on the right for it to be lower than. And so, no, we would not include that as a local minimum. All right, so now looking at this graph, what I want to think about in particular is that at each of the local maximums and minimums, what is the derivative going to be at each of those? So let's start with the local maximums. So I have a local maximum here and here. What's the derivative at point B there? Well, it looks like it is flattening out there, so that like our slope is going to be at 0 there. So there, our derivative would be 0. And if we take a look at D there as well, the slope at D, therefore its derivative, would also be 0. All right, what about at the minimums? Well, we got a local minimum here at C, and we have a local minimum here at E as well. What is the derivative at C? Well, actually, this is almost a little bit of a trick question. There is none. It's not 0. There is no derivative at part C. The curve at part C is a point. It's a corner on the curve. And so remember that at corners, our graph is not actually differentiable. All right, what about part E? What is the derivative at E? Well, there it is differentiable. It would be a horizontal slope there. And so there our slope is 0. And so you notice that we can have local maximums and local minimums happening in a few different ways. It can happen certainly when our slope is 0. Notice there are no other places here where the slope was 0. So everywhere where the slope was 0, it was a local maximum or minimum. But it can also happen when the derivative does not exist. These points are called critical numbers. And we're going to be working a lot with critical numbers here going forward. So please add this into your notes. And so you'll notice as you wrote this down that we have this piece of information here. If we know that a particular point is a maximum or minimum, then we know that that is also a critical number. Does it work the other way? If it's a critical number, will it also be a local maximum or minimum? And there, the answer is no. Because this can happen just anytime the derivative does not exist. And as we saw in some of those previous examples, if I have a jump in my graph, maybe something that looks like that, that is not a local max or min. And so that detail about the derivative not existing can cover a lot. Now, do you remember all the different ways that the derivative cannot exist? We talked about corners. Do you remember the others? We could also have different types of discontinuities like jumps, holes, or asymptotes. Or we could also have the rare vertical tangent as well. And so to practice the idea of critical numbers in particular, take a look at this graph, figure out what is the derivative at each of the critical numbers. Now, a big part of this particular practice problem is that I'm really wanting to make sure that you recognize what the critical numbers are. And there's actually a lot of critical numbers here. This is a critical number because the derivative at that point does not exist. So this is a dne. Here at 0, the derivative also does not exist. Then here at 2, that is also a critical number. This is actually a jump discontinuity, and so that would be does not exist. All right, here we have a critical number over at 3. There the derivative does exist, it's going to be 0. Then at 4, our derivative does not exist because it's a corner. And then at 6, our derivative is back to 0. And yes, at 7, that would also be a critical number. In that case, the location where it does not exist. Now we're not just going to work from graphs though. We're also going to be working from the equations. And so here's an equation, and we're going to figure out where the critical numbers are of this particular equation. Now remember, the critical numbers occur any place where the derivative equals 0 or where the derivative does not exist. So the very first thing we need to do here then is we need to figure out what the derivative is. And now we need to figure out where does that derivative equal 0 and where does it not exist. And I'm actually going to answer that last part first because looking at this is a polynomial function. And polynomials don't have any discontinuities in them, any non-differentiable points. It's actually differentiable for every single point in its domain. And so we aren't going to have to do any worrying about places where it does not exist. So really then we can just focus on places where this derivative equals 0. So I'm going to set the derivative then equal to 0. And then once I've done that, then we solve it. And seeing as how I'm looking at a quadratic here, I'm going to want to solve this by factoring. And thankfully it is factorable, so we don't have to resort to quadratic formula. And now that I've factored it, I can say what x would actually equal here. So x would equal 5/3 and -3. Those would then be my critical numbers. And yes, we could expect that there will likely be a local maximum or a local minimum at each of those values, but that is something that we'll delve into a little bit more deeply coming up later. All right, next up, let's take a look at an equation that's maybe a little bit more complex. Just like with the last one, if I'm going to find the critical numbers, I have to figure out where the derivative equals 0 or where the derivative does not exist, which again means the very first step is to find the derivative. Now in this case, there actually are going to be some places where we got to think about where it's equaling 0 and where it does not exist. In order to see those a little bit more easily, you might prefer to actually rewrite this particular derivative equation by getting rid of those messy parts of the exponents, the negative and the fractions. And so if I want to get rid of that x to the -2/3 and simplify that down a bit, remember that a negative exponent flips it in the fraction, so that becomes x to the power of 2/3 in the bottom of the fraction. But of course x to the 2/3, I can also change that into radical form, and so that would become the cube root of x squared. And so that's the way I'm going to write it up here. So then this first part just becomes 1/3 cube root of x squared. And then do the same thing with the second term as well. So my x to the -5/3 is going to become 1/the cube root of x to the 5th. And so then my second term is going to be 2/3 times, because of the 2/3, then that cube root of x to the 5th. So then where does the derivative not exist? Well, basically about the only ways that we're going to have places where something does not exist is where we either try to take like a square root or any even root of a negative number. Well, we don't have that here. They're odd roots, so we don't need to worry about that. So the other way that we can end up with it not existing is if we try to divide by 0. And since x is in the denominator here, it is possible to have us divided by 0 if we aren't careful. So if I take a look at this term, what would I have to plug in for x in order for us to be doing 1 divided by 0? Well, it'd have to be 0. because 0 squared is 0, and the cube root of 0 is 0, and 3 times 0 is 0. And so here we can see that x cannot equal 0. If I take a look at this, I come to the same conclusion. So in both terms, I find that x cannot equal 0, and therefore I can already know that I have a critical number here at x equals 0. But it's not going to be my only critical number, because I can also try to set my derivative here equal to 0. And while there are multiple methods that you might use for solving this particular one, and yes, you're free to use any of those that would work, I think probably the way that would be most intuitive and most user-friendly for a lot of people would be to move one of these fractions to the other side, and then we'll have a proportion that we can cross multiply. And so I grabbed this term and I subtracted it from both sides. And now I can go ahead and cross multiply in this particular part. And now that I've cross multiplied, I can now go ahead and start getting those x's to the same side. So in order to do that, I'm going to go ahead and divide both sides by one of the x's parts. So I'm going to divide both sides by the cube root of x squared here. And while that looks kind of scary to do on the right-hand side there, it's actually not too bad, because remember that the cube root of x to the 5th was really just x to the 5/3. And if I'm going to divide that by the cube root of x squared, that means I'm dividing it by x to the 2/3. And when I divide x's, I subtract their exponents. 5/3 minus 2/3 is 3/3, or in other words, 1. So that's just 3x. Much simpler than it looked like it might have ended up being. So last step, go ahead and divide both sides by 3, and you'll find that x equals -2. And so that is our other critical number. So here x equals 0 and -2. And that's our final answer. Now that we know that, what do you suppose is happening at 0 and -2? Think both of those are going to be local extrema? Well, let's actually take a look at the graph here for a moment, just so you can kind of see that piece in action. This is the graph of this particular equation. And so you'll notice here is our -2. So notice that our graph is leveling out there. That's where our derivative was 0. You can see that that is a local maximum. But at 0, notice what we seem to have going on there. There it's an asymptote. So we would not actually have any extrema happening there at all. It's just an asymptote.